Hello, welcome to this lesson in the Linear Algebra Tutor. In the last section, we introduced the concept of an augmented matrix to represent a system of equations. We also introduced the legal row operations that you can do to an augmented matrix that preserves its integrity, so to speak, and lets us solve a system of equations by row reduction. I know that it was coming fast and furious, and watching one example is never going to make you an expert. So what we'll do now is we'll solve a second example and give you a little bit more confidence with using this technique. So if we have a system of equations, x plus 2y minus z is equal to 1, and then we also have x plus z is equal to 3, and then we have x minus y is equal to 2. Again, we have three variables, x, y, and z, but we only have, I should say we have three equations. So because of that, we're reasonably hopeful that we'll be able to use row reduction to find a solution, but we won't know until we get to the end. So let's write this as an augmented matrix. So we have the coefficient matrix for the first equation will be 1, 2, and negative 1. Put our augmented dotted line and stick a number 1 over here. Now for the second line, since x is here, we have a coefficient of 1 there. There is no y in the second equation, so we have to put a 0. And then we have to put a 1 for z, and then we put a 3. And then there's a 1 for this x, there's a negative 1 for y. There is no z here, so we'll put a 0, and then we'll put a 2. The important thing to do here is you need to pad your matrix with zeros where appropriate. I'm kind of showing you that as we go along here. All right, now the first thing we usually want to do is, we want to transform the left-hand side to an identity matrix with 1s on the diagonal and 0s everywhere else. I already have a 1 in this location, so I don't need to do any row switching or anything. I'm very happy that that's already there. So because I've already done that, then we need to plan our next move. And our next move is going to be, we're going to keep the top matrix intact, or the top row intact, I should say. Now we want to get zeros underneath our 1 here. We want to get zeros for both of them. So on the second line, I want to take negative r1 plus r2. I want to take a negative 1 and multiply it by these elements and add it below. When I take negative 1 times this and add it here, I get a 0. Negative here and then add it here, I get negative 2. Negative times this gives me positive 1 plus this gives me a 2. Negative here plus this gives me a positive 2. So far I'm doing well. And again, I want to put a 0 here, so I'm going to do exactly the same thing. Negative r1 plus r3. When I put a negative times this added here, I get a 0. Negative times this added here, I get negative 3. Negative times this gives me positive 1, plus that gives me 1. And then negative times this plus this gives me a positive 1. So I've achieved success in that I have a 1 on my upper leftmost element, and I have zeros underneath it. All right, now the next thing I want to do is part of my little algorithm. I told you that's sort of my little efficient way of doing things. I'm going to preserve the top. I'm not going to do anything to that. Next thing I want to do is make the middle number, the next guy on my diagonal, a 1. So basically what you're doing is you're trying to get first this guy to match exactly what you want, 1, 0, 0. Then you want to get this to be a 1, then you want to get this to be a 0, then you want to get this to be a 1, and then you work on the zeros up above the diagonal. So to get this to be a 1, all you have to do is say negative 1/2 times row 2. Negative 1/2 times row 2. So when I say negative 1/2 times this, it's still going to be a 0. Negative 1/2 times this would be a positive 1. Negative 1/2 times this will give you negative 1. Negative 1/2 times this will give you negative 1. And I'm going to leave the bottom alone. 0, negative 3, 1, 1. All right, now that I've achieved success in that, what I want to do next is leave the top row alone. 1, 2, negative 1, 1. The middle row I also want to leave alone. 1, 0, 1, negative 1, negative 1. And then what I want to do is make this guy a 0 under there, and I'm going to do that by multiplying this times 3, positive 3, and adding it to here. So the way I'm going to write that is 3 times row 2 plus row 3. 3 times this middle row times the third row. Obviously here I'm just going to get 0. 3 times this added here, I'm going to get 0. 3 times this gives me negative 3, added here, get negative 2. 3 times this gives me negative 3, added here, I get negative 2. All right, so I'm getting much better. I've got zeros down below here. I've got 1s along the diagonal. The next step is to put a 1 here. So what I'm going to do now is I'm going to basically just say that what I need to do in the next step is I need to multiply this row here, the third row, by negative 1/2. Negative 1/2 is going to give me a 1 right there. So let me move on over here to my new matrix. I'm going to write the first part of the matrix exactly the same. I'm not doing anything. 1, 2, negative 1 with 1. Haven't done anything to that. The middle row I haven't done anything to it as well. All right, and the third one, once I multiply by negative 1/2, so I'll say negative 1/2 times row 3. Negative 1/2 times row 3. Then, since these were zeros, they remain zeros. This guy becomes a 1. When I multiply negative 1/2 times this one, I also get a positive 1. So that goes down there. So now I'm sitting pretty because I have 1s along my diagonals and zeros down below. All right, next, I want to continue on down and say, now I want to work on getting zeros above in my third column right there. All right, so in order to do it to the top, and since this is already negative 1, this is already positive, all I want to do is say row 3 plus row 1. I don't need to multiply by anything. I just need to add it like that. So when I take this and add it to this, I get a 1. This and add it to this, I get a 2. This and add it to this, I get a 0. This and add it to this, I get a 2. Okay? And then for the middle row, again, this is already a negative here. So I'm going to say row 3 plus row 2. Add this together, get a 0. Add this together, I get a 1. Add this together, I get a 0. Add this together, I also get a 0. And the third row, I'm actually not touching at all, 0, 0, 1, 1, and now I've arrived at that. So I've gotten zeros on top of my third column intact. And now, for the last thing, what I'm going to do is make this into a 0 by saying negative 2 times row 2 plus row 1. Negative 2 times this plus this, I get a 1. Negative 2 times this plus this, I get a 0. Negative 2 times this plus that gives me a 0. Negative 2 times this plus this still gives me a 2. And then the rest of it stays exactly the same. All right, so a little bit less painful than the last time, partly because we have a pretty good understanding of what we're doing now. Now I have an identity matrix, 1s along the diagonal, 0s everywhere else. Whatever falls out of the right-hand column is what happens. And now we're saying that this augmented matrix exactly is equivalent to the original one we started with. So I can say that x is equal to 2, y is equal to 0, z is equal to 1. So that's how I do each individual variable, or I could say matrix x is equal to 2, 0, 1. You can think of it as a column vector. You can think of it as a column matrix representing the individual values of the variables that we care about, 2, 0, and 1. And because we get a unique solution here, we call this system consistent. Again, if we cannot find a solution, which I'll show you an example of in a minute, then we call it inconsistent. But when you have a solution, you call it consistent. All right, so going back over just one more time quick, you want to get, first thing is a number 1 in the upper left-hand corner. Then you work on zeros directly below that. All right? Then you form a 1 in the very center of the matrix. Then you find a 0 under that. Then you make a 1 in the next part of the diagonal, right? And then you work on getting zeros above that. Zeros above that, then you work on getting a 0 above the last guy. That's basically what it is. Now, also keep in mind that so far we've just been doing 3x3 matrices, just to kind of teach you a little bit how to do this. I don't really want to work too much with 2x2 matrices because that's so trivial that you don't get the full experience. 3x3 matrices requires several steps, so you kind of get an exposure to it. Now, if you go to 4x4 matrices, it takes a lot more steps because you have 4 elements on the diagonal, but you would still be trying to do the same thing. You would want 1s along the diagonals, 0s above, 0s below, and if you had 5x5 or 6x6, you're going to be working a long, long time, but the end result would be the same. You would want 1s on the diagonals, 0s everywhere else. Whatever fell out on the right-hand side would be what we call your solution. So far, we have had consistent solutions, which are basically systems of equations that have a solution, right? But it's very possible that your system, even if you have enough equations, may not have a solution at all. And so we'll show you an example of that in just a minute. And what's going to end up happening is when you do your row reduction operations, you'll find out some weird things fall out at the end here. See, here it's very clear because you have something that goes along with x, something that goes along with y, something that goes along with z, and it makes total sense. But in the next example, we're going to show you that sometimes you'll have an inconsistent set of equations, which means it doesn't have a solution. And so let's go look at that in the next section.